Okay, good morning, Lamai. Today we are discussing our evaluation test paper 2. Okay, so this paper MCQs we are going to discuss now. In this MCQs we have 30 MCQs and those are from unit 1 to unit 4, right? That means from atomic structure, then bonding and structure, then chemical calculations and the fourth lesson, gaseous state of matter. Those 4 lessons are checked in this MCQ discussion, right? So what I'm trying to do here, I'm going to take more time today for the discussion because I need to tell you exactly how to answer these MCQs and if there are any theories missing to you, okay? Let's say some theories are there, you can't understand how those theories are related to this MCQ. So I want to bridge that gap. Okay, so therefore I'll be explaining this one extensively. So we'll see how it goes, right? And if you have further questions during the discussion, you can send them as a message so I can answer and at that point to our discussion also, right? So we'll do a very productive discussion today, right? So what you need to do is please write a good review for this MCQ discussion because in our exam, nearly 90 students face the exam, right? In this exam, right? Then out of 30 MCQs, only one student got 27 out of 30, right? That means that student also has 3 MCQs to understand, right? But others, the higher mark students were there, like around 22 marks, 23 marks, 24 MCQs, like that. Okay, so that means everyone has something to improve. Okay, so take this as a chance and write a good review and don't stop there. Okay, you need to revise this. That is the other mistake we make. Okay, so we do papers, we write reviews, but there's a question whether we revisit that one, whether we study that part again. Okay, so let's add that also to our discussion. Understood? So then by the time, okay, so little by little you will get improved. Okay, because all these MCQs are exam level questions and some of the past paper questions also I added to the paper. So that means a good paper, right? So it's okay to have doubts, it's okay to have mistakes, but that's why we have time until 2027 A level to improve that one and to correct them. Okay, so let's start the discussion. I'll show you the paper. I'll show you the paper. So when I'm uploading this to YouTube, I'll add timestamps. That means you can easily go to any MCQ you prefer. So I'll make sure that happens. Okay, so let's do the discussion properly and let's start the discussion from the first MCQ. So it is asking, which of the following is not related to Ernest Rutherford? This is a shadow question from this year, 2025 year A-level MCQ. So it asks about the radioactivity in the 2025 A-level exam. So radioactivity was discovered by Henry Becquerel, right? And that's it. About radioactivity also, our Ernest Rutherford, our shadow question, that's why I targeted to asking. Most of the students I saw selected radioactivity, right? For this answer, that means Ernest Rutherford, they are thinking Ernest Rutherford is not related to radioactivity. That is wrong. Understood? Ernest Rutherford is related to radioactivity. I mean, he didn't discover radioactivity, but he did a part of the theory of the radioactivity. That means he's the one who discovered alpha, beta, gamma radiation. Understood, Lamai? Ernest Rutherford is the one who discovered alpha, beta, gamma radiation. Okay, so he didn't discover radioactivity, but he identified alpha, beta, gamma. Okay, so first thing we are going to do today. So take this MCQ and you have to say radioactivity is related to Ernest Rutherford. Okay, and say how it is related. Okay, so how this radioactivity is related to Rutherford by alpha, beta, gamma radiation. Okay, so right in front of the second one. Okay, so second answer is true. Why? Because radioactive alpha, beta, gamma, 3 types of radiation was discovered by Ernest Rutherford. Understood? And add a sentence to this one. But radioactivity, that is also worth. Radioactivity is discovered by, was discovered by whom? Henry Becquerel. Henry Becquerel. Check the spellings and write. Understood that one? So that's the point. That's one of the most important points in the first MCQ. Right. Then look at the other points. Now we need to find exactly which area Rutherford is not related. Right. Now look at the other answers. Nucleus of atom. So is he related to nucleus of atom? Of course, yes. Right. Because he is the one who presented this nuclear model of atom. Right. So before Rutherford, so there was the J.J. Thomson model, the Plum-Pudding model about atom. So it says there is a positively charged sphere and negative electrons are embedded there. But when Rutherford and his two students, Geiger and Marsden, did an experiment called gold foil experiment, which is given as our third answer, right? So when they did this gold foil experiment, they did a great discovery that most of the space of the atom is empty because most of the alpha particles used in this gold foil experiment penetrated the gold foil without any problem, right? That means most of the space of this atom is empty, right? So that means, okay, so there's a small positive dense place which Rutherford later called as nucleus in the atom. Understood? So our second and third dance, sorry, first and third dances are, you can combinedly say what? Nuclear model of atom. Nuclear model of atom. So then you can draw a small picture about the nuclear model of atom. So Rutherford said that electrons are randomly moving around this positive nucleus, and he said that most of the space of the atom is empty. Understood that one? So this is nucleus. This is nucleus. He said that nucleus is a positive small place. And later, after several years, he discovered what exactly this positive charge is given. From exactly which is positive charge is given. So he later discovered the proton. That was his last discovery. Proton, right? The smallest positive charge. Understood? Smallest positive charge. So let me show you the reaction relevant to that one. Give me a second. This one. This is the reaction. Can you see? This is the nuclear reaction Rutherford did. This was actually the first documented nuclear reaction. Okay, so Rutherford actually did a very great contribution to the development of physics as well as chemistry. Okay, so this reaction you need to write. Okay, and you can see it is balanced. Alpha particle can attack a nitrogen nuclide. Okay, and then it can give oxygen 817 nuclide, then H11. What is this H11? Hydrogen nucleus. Okay, so protein, or you can say proton. Understood? So that's how Rutherford discovered proton. Okay, so there is a story behind this one. So some many technical terms are there, but just understand this is also not there in your syllabus. But nuclear reactions we study, So therefore, it's good to write this reaction and kind of reminding you the nuclear reactions also. And Rutherford is the one who did this experiment and found the proton. So that's about our first MCQ. You can see, okay, Rutherford is related to these areas. Okay, so let me finish the discussion by the answer. So you can see in this PDF, the answer is answer 5. So he is not related to energy levels of nucleus. So energy level concept was presented by whom? Niels Bohr. energy level concept. He said that electrons are moving in energy levels. Energy levels. So let's say if this electron is here, so it has this certain energy. Okay, so this is n equal 1, first energy level, second energy level, third energy level, like that. So according to Niels Bohr, right, in a given energy level, there can be a specific number of electrons. For example, in the first energy level, you have 2 electrons. In the second energy level, you have 8 electrons. In the third energy level, you have 18 electrons. Like that, it continues. The next one, you have 32 electrons. Understand? So then when these electrons are moving in a given energy level, they have a specific energy. Okay. So then again, Bohr used this model. This is called as energy level, or you can say Bohr model, right? He used his model to explain hydrogen emission spectrum. Remember, hydrogen emission spectrum. So when you take hydrogen, hydrogen has only this single electron. So this electron can absorb energy from electromagnetic radiation and jump to the next or the even a higher energy level by absorbing energy. Okay, then absorption spectrum is given. So then these electrons can descend back to, can come back to lower energy levels. So when that happens, what spectrum is given? Emission spectrum is given. Can you understand? Like that, he used this model to explain hydrogen emission spectrum. So right now, since you are learning theories quickly and you are learning a lot of new theories now, it's very important to link the new theories to already learn theories. Okay, so for example, this is not a new one, right? But you know, energy levels are presented by Rutherford, no? Sorry, Niels Bohr. So then you need to link that theory to the hydrogen emission spectrum. Then you can remember both easily. Understand? So do that one. So like our answer is the fifth one. Energy level concept was presented by Niels Bohr to explain what hydrogen emission spectrum. Okay, write that as a sentence in your review. Energy level concept was presented by Niels Bohr in his model to explain hydrogen emission spectrum. Okay, right. So later there's a MCQ. We will discuss about emission spectrum also, but right now this will be enough. Okay, let's go to the second MCQ. In the second MCQ, you have which of the following set of quantum numbers is not represented by an electron in Fe or iron atom. Fe, iron. So this question is really easy, and to get an answer, you don't need to write the electronic configuration of iron, right? If you just simply check the given quantum sets, you will understand there is one quantum set which is incorrect. Okay, there's one quantum set which is incorrect. So I'll come to that one. But before that, I'm going to quickly remind you what are the quantum numbers. Okay, this will be helpful for you. But if you feel you need more to remind this one, let's say, I'm just briefly discussing this one here, right? Briefly explaining you the quantum numbers, right? So when you want to learn it more, right? When you revise it more, you can just go to your note and you can go to the recording and see if you need the full discussion, right? So I'm going to quickly tell you what are the quantum numbers and how it is related to this question. Okay. So in quantum theory, it is the theory we accept now for the atom in our A-level syllabus, right? So it says electron is basically not moving in any path, right? So a Bohr model was rejected, and then this quantum atomic model was established, right? And it says this electron is not moving in any certain path. It is kind of random, right? And in a given space, okay, in a given space, the probability for the existence of electron is high, right? So for example, s orbitals, p orbitals, d orbitals, like that. There are different shapes. You know, s orbital is a spherical orbital. Okay, so within that spherical space, there is a higher chance of existence of this electron. 99% chance. Understood? So that's how the quantum model is basically established. You can just understand. Bohr model says electron can move in a certain path, but our quantum atomic model says it's not a certain path. It's a definite three-dimensional figure. Let's say maybe a sphere or maybe a dumbbell shape, right? Within that space, electron can exist in any place, right? So 99% chance, that means it can exist. There's a chance of 1% chance of existing that electron even outside that sphere also. Understood? Something like that. Okay, so it's kind of the actual equations and everything in quantum atomic model is kind of very complex. But to explain it briefly for everyone to understand, we use 4 quantum numbers. Okay, 4 quantum numbers. That means with these 4 numbers, we can predict, we can get an idea regarding where this electron might be. Understand? So like that, it's now getting a little bit complex, no? Complex than Bohr model. Bohr model just simply say electrons are moving in certain path, but this one says it is not, right? So to explain that easily, we use quantum numbers. By those 4 quantum numbers, it is just like an address, right? With those 4 quantum numbers, you can say where this electron will be. Understood? So now, what are those 4 quantum numbers? We have M, L, Ml, and Ms. These are the 4 quantum numbers. So this is called main energy level. This is called sub energy level, and this one is this is called main. This is representing main energy level. This is representing sub energy level, and this one will be representing orbitals. Orbitals, or you can say orientation. Orientation of orbitals. Okay, and then this is representing spin of electrons. Okay, so there are names for these quantum numbers. For example, the first one is called principal quantum number. Principal quantum number. And this one is called azimuthal quantum number. And this one is called magnetic quantum number. And this one is called spin quantum number. Understood? Right. Then you need to know what are the possible numbers that they will have. That's how you select the answer for this MCQ. Okay, so like I said earlier, there is one incorrect quantum set, no? Right? Quantum set, no? Right. Like that, possible numbers for the main energy level is n can be, they are from 1, 2, 3 up to infinite energy levels. Okay. And then for the sub energy levels, L values can be there as, let's say L values can be there as 0, 1, 2, 3, like that. Okay. So 0 represents S sub energy level, which is a spherical orbital. Spherical orbital. Okay. And 1 represents P sub energy level. P sub energy level. 2 represents D sub energy level, and this one F sub energy level. Okay, P, D, those are dumbbell shaped orbitals. Dumbbell shaped orbitals. Actually, the shape of D and F might be different, so it's not there in our syllabus. Just say some shape is there. That's enough. And then, okay, so let's say when you start a quantum set by telling 2, 0, that means the first quantum number and the second quantum number are 2 and 0. That represents what? 2s sub energy level. Understood like that? That's why we say by azimuthal quantum number, you can say sub energy level. Is that clear, Laman? Right. Then, what is this ML? ML. ML is representing you the orbitals, the number of orbitals that it can be there. Okay. For S sub-energy level, you have only one orbital, only one S spherical orbital. And for P sub-energy level, there are three dumbbell-shaped orbitals oriented perpendicular to each other. Like that, for D sub-energy level, you have 5 orbitals. Okay. So then the special thing here, each orbital has a number. Okay. So that number for the S sub-energy level will also be always be 0. And for the P sub-energy level, you have to have 3 numbers. No? So then if you can say 0 here, then it will be -1 and +1. Can you see? You can easily label the 3 orbitals. That's why at the first place, we selected number 1 for the P sub-energy level. Because if you say -L to +L, then you can easily label it. Let's see whether that theory applied here. -2, -1, 0, +1, and +2. See? Nicely you can label it. Okay, so our purpose is telling the location, okay, possible location of electron quickly, that everyone can understand. Okay, right. And then the spin represents, now each orbital can fill up to 2 electrons. Those 2 electrons are spinning to the opposite directions. Okay, so we label the clockwise spin +half, anti-clockwise spin -half. Okay, so if they say a quantum set, it will be like this: 2, 0, 0, -half. That means what? The 2s electron that is spinning to the anti-clockwise direction. Understood? So 3, 2, -1 +half. That means 3, 2 means 3d. Okay, 3d and in this orbital, -1. And it is spinning to the clockwise direction. Like that, you can explain where this electron will be. Understood? It is more improved version, or it is more advanced thing than the Bohr model. Bohr model just says about the energy level. If they say third energy level, it can be basically any electron in third energy level. Maybe 3s, 3p, 3d, we don't know. But in the quantum atomic model, it is explaining more. Understood? So then again, you need to understand, look at the question. No, before going to that one, I'm going to tell you one more thing. Now, all possible, any given quantum set may not be possible. For example, like we said, in the first energy level, you can keep up to only 2 electrons. No? So then in the first energy level, you have only s orbital. Only s orbital, right? You don't have any p orbitals or d orbitals in first energy level. Understood? So if someone start a quantum set by telling, let's say 1, 2, -2, +half or something, that is definitely wrong. Why? Because 1, 2 means 1d. 1d is not existing. That's a wrong quantum set. Get the idea? So like that, you can check the validity, whether it is actually there or not for a quantum set. Okay, so that's how it goes. Okay, so then what are the possible quantum set? Quantum sub-energy levels. Then you can say 1s is there, 1s is there, 1p, those are not existing. It's wrong. So then you have 2s, and second energy level has 2s and 2p. Okay, third energy level has 3s, 3p, 3d. Understood? Then fourth energy level has 4s, 4p, 4d, 4f, like all the quantum, all these 4 are there. Understood? So like that, you need to check whether the given quantum set is a possible one. Now, go to the answers. I'll show you the answers. Now, these are our answers. Check this one. Now, 1 means 2p. 2p is there, no? 2p is a possible quantum set. Then look at the second answer, 30, 3s. It's also an existing one. 40, 4s is there. But 2 means 2d. 2d is not an existing quantum set. Only second energy level has 2, 0 and 2, 1. That means 2s and 2p. Now you can understand. So 2 is not a possible number. So it's wrong. That's how you select the answer. Okay, in the fifth answer you have 3, 1. 3, 1 is also existing. Understood, Lamai? 3, 1 is also existing. Right? Okay, so now I hope you got the idea. Right? I hope you got the idea. Then they are asking about iron atom. So like I said earlier, you don't need this iron atom to find the answer. But still, it's good to review that also here. So you can write the electronic configuration of iron atom according to A-level syllabus. Okay, so when you write the electronic configuration, okay, so what do you need? First of all, you need to know how many electrons are there in that given atom. So if it is iron, you can find its atomic number from the periodic table. You will be given a periodic table in the exam. And if you check iron, you will see 26 is there. So 26 is the atomic number of iron. That means you have 26 protons and you have 26 electrons in the neutral iron atom. Okay, so then you need to write how those 26 electrons are arranged according to the quantum atomic theory. Okay, so we are discussing here about sub-energy levels now. So then you are representing it like this. 1s2. 1s2 means what? In the 1s sub-energy level, you can fill up to 2 electrons. 1s2. That's it. Then 2s also, on always s sub-energy level, you can fill up to maximum 2 electrons. 1s2, 2s2. Then 2p6 means what? In p sub-energy level, you have 3 orbitals now. In one orbital, you can put 2 electrons now. So then in 3 orbitals, you can fill up to 6 electrons. So 2p6, like that. Then 3s2, 3p6, then 3d6, 4s2. So there's a small difference. In 3d, you can fill up to 10 electrons. But here you can see the configuration. Before filling 3d, 4s is filled. So what's that theory? What's that theory? You had to write. What is the name? Aufbau principle. Okay, so even though electrons are there like that, energy levels are there like that, they are not always filled gradually. They are not always filled in order. So actually they are filled according to the Aufbau principle. What is this Aufbau principle? Aufbau principle says electrons are filled to their sub-energy levels in the ascending order of their energy. Ascending order of their energy, right? So that means first of all, 1s is filled, then 2s, 2p, 3s, 3p. But before filling 3d, what is filled? 4s is filled. So 4s is having lower energy than 3d. Okay, so that you need to know as a fact. Okay, you can't say why it is happening, right? So it happened, right? 4s is having a lower energy than 3d. Okay, so 4s should be filled before 3d. That's why in that configuration you saw 4s2 filled before filling 3d. Okay, so that's why remaining 6 electrons were moved to 3d sub-energy level. It's very simple. Okay, so right, the thing I said now, most of you are here now are maybe familiar with, right? But still, if there is a kid who don't understand this, I mean, let's say he or she forgot this, right? So then by listening to this and going through the theory not one more time, you will be perfectly able to understand this theory. Okay, so do it, right? That's my advice. So don't wait until the last minute like you did in O levels. You can't do any magic here, okay? So the magic here actually is consistency and persistency, right? Because let's say you get low marks in an exam, you should be persistent. You should not give up until you get better. Understand? So if you give up, okay, I got low marks, I can't do this, then it's better to give up right now because you have enough time until 27 A level. You can select another stream and do, right? But if you are facing science and maths, it is hard. You knew that one from the very beginning. That otherwise, if you are not ready to face that challenge, you will not select it. Ne? Understand? So then think about that. Why you selected science or maths for the A levels and act according to that. Okay, it's hard, I know, but you also have to give you 100% to that one. Okay, right. So that's the answer. Answer 4. I hope you got that theory point about the quantum number and electronic configuration I explained. Aufbau principle is one theory related to electronic configuration. So I'll tell you just the names of other theories. You can go through the note and find out them. For when you write electronic configuration, you need Aufbau principle, and Pauli's exclusion principle also you need. Why? Because Pauli's exclusion principle says you can maximally fill 2 electrons to a given orbital. Okay, that's why 1s2 was there. That's why p6 was there. Why? Because you can't fill more than 2 electrons to given orbital. Okay, so that said by Pauli's exclusion principle. And there's one more principle when you need when you draw orbital diagrams. What is that? That is called Hund's principle. Hund's principle says, right, when you fill electrons to a given subenergy level that has degenerated orbitals. What are these degenerated orbitals? Subenergy level is divided into several orbitals. Example, P subenergy level, D subenergy level, and so on. So in P subenergy level, it is divided to 3 orbitals. Okay. So then when you fill that 3p orbitals, first you are filling 1 electron per each orbital. Then they get paired. That's the idea. A subenergy level is not an degenerated orbital, not a degenerated orbital. Okay, so that theory is not applied to that. But for P, D, and so on, it's applied. Okay, so like that, I know you can get a perfect idea. Okay, so if you talk about the first unit, okay, if you talk about the first unit, you have 2 main areas in the first unit. What are the 2 areas? The theories and discoveries about atomic model. Okay, atomic model. So these 2 questions we discussed here is related to atomic model. First one is related to atomic discoveries about the scientist and all. And the second one is the electronic configuration, quantum atomic model, the newest one. Okay, so then that's the first part of the atomic structure lesson. And the second part is what? Periodic table and periodic properties. So there are several MCQs in this paper. We'll see that also when we go there. Right, so I hope it is very much clear to you. Now let's move into the third MCQ. Oxidation numbers of central atom of the ions, chromate, nitrite, carbonate, and sulfide. Now, since we did IUPAC nomenclature of simple inorganic ions and compounds, you should be able to tell the names like I said. Okay, so you can go to that note. It is there in the third unit. At the end of that you will have IUPAC nomenclature theories, right? The system, the rules are there. So you can revisit that one and catch the names that are given for these 4 ions. Okay, so I'll tell one more time: chromate. Then you have nitrite. Then you have carbonate. And finally you have sulfite. Okay, right now they are asking not the name, they are asking the oxidation number of the central atom. So how do we get this oxidation number? What is meant by oxidation number? I'll explain I'll explain a little bit about that one, about the oxidation number. So simply, you have proper and exact definitions in your tute. Okay, just for the review, I'll tell. Oxidation number is the number of electrons. Oxidation number is the number of electrons, right? That lost or gained totally or partial. Totally or partial. Okay, simply. So if it is a lost, you assign a plus sign. If it is a gain, you assign a minus sign to the number of electrons. Let's say there is an atom when it is becoming 2 plus ion, it loses 2 electrons. So it lost 2 electrons. So oxidation number is also plus 2. That means if it is an ion, monoatomic ion, monoatomic ion, so sodium plus Cl minus like that, okay? Single atom. If it is a monoatomic ion, oxidation number will be equal to its charge. Understood? Oxidation number will be equal to its charge. Sodium plus oxidation number is plus 1. Like that. Simply says how many electrons it lost, okay, totally or partial. So here it is a total electron lost because sodium plus is losing the electron fully, no, completely, no. That's right. Understood that completely. Okay. So now here it's not, those are not monoatomic ions. So, but anyway, I'll tell about monoatomic ions. If it is a monoatomic ions, let's say sodium plus, it is plus 1. If it is a Cl minus, it is minus 1, like that. Now here, those are polyatomic ions. Polyatomic ions. The theory is, in polyatomic ions, the sum of oxidation numbers is equal to its charge, overall charge. Understood? Sum of oxidation numbers is equal to its overall charge. That's the theory. Sum of oxidation numbers is equal to its overall charge. Okay. So now let's take our example carbonate. CO3 2 minus was there. So how do we decide the oxidation number of carbonate? So there are two methods for that one. Okay, two methods for that one. So what is the first method? First method, you can get the Lewis structure. And then you can mark dipole moments. There are other methods also, which I saw some methods are described in your resource book too. It's also correct. You can understand that too, but doesn't matter what is the method. Okay, so what I told you is this one. You can mark dipole moments, then decide the oxidation number. Then you can go to the oxidation number. So how do we do that one? Like it says, first we need the Lewis structure. Okay, so Lewis structure is a topic you learn in the second lesson, the very first topic you learn. So you should have the ability to draw any given structure of a molecule or an ion like this. Okay, so what is the structure of carbonate? What is the structure of carbonate? So I'll explain a Lewis structure in a later question, but I'll just get the structure for this one. Okay, so this is the Lewis structure for the carbonate ion. You have negative charges on oxygen. Okay, so then they are telling us to mark dipole moments. So what are these dipole moments? It's simply an arrow that represents how electrons are pulled for a given orbit. So now this bond between carbon and oxygen, okay, that actually shows 2 electrons. No? Single bond is and 2 electrons. So here you have 2 dashes, that means 4 electrons, a double bond. So these electrons are more attracted to, understand this well, these electrons are more attracted to more electronegative atom. So electronegativity simply means the ability to attract these electrons. So who's the more electronegative atom? Is it oxygen or is it carbon? It's oxygen, right? It's oxygen. You know that one from even O levels. Because oxygen is a small atom than carbon, it has more nuclear attraction than carbon. So when it makes a bond, oxygen has a very good ability to attract those electrons toward itself, right? So oxygen is more electronegative than carbon. So then it will attract these bond electrons toward itself. So we represent that one like this. Okay. And then there are 2 dashes. So we should draw 2 arrows like that. That this is dipole moment. So there are many other uses of dipole moment. I'll explain them during the discussion. But right now, it can be used to find oxidation number also, right? So oxygen is attracting electrons like this. Now you can see it represents actually losing and gaining, no? Isn't it? Now you can say about this carbon. You can say about this carbon. Carbon lost 4 electrons. Now it is a partial losing. It's not an iron. Understood? Carbon doesn't have +4 charge, but instead of that, it has a delta charge, small charge. Okay? And it is losing 4 electrons partially. So therefore, what is the oxidation number of carbon? If it is losing, oxidation number is positive, and it partially lost 4 electrons, so oxidation number is +4. Understood that one? Oxidation number is +4. Now take this oxygen. This oxygen, it gained 2 electron partially. So oxidation number should be -2. Okay. And then look at this oxygen. What is the oxidation number of this one? Don't say -1. Why? It gained 1 electron partially. True. Right? But didn't you notice the negative charge? Negative charge means what? It already has gained 1 electron total. Understood? Total electron gain is also there. So 1 electron totally, 1 electron partial. Partial gaining and total gaining is there. So ultimately it gained 2 electrons. So therefore oxidation number is what? -2. Yeah, that is not difficult. I mean, these theories are not difficult. Right? Well, හැමෝටම පුළුවන්, right? Anyone can understand this. The thing is you don't practice. Right? අර මම මතක නැත්තම් practice කරලා නැහැ. ඒකයි ප්‍රශ්නේ, right? So let's practice this. Okay. Right. Now you can apply this method to get the other, draw the other Lewis structures and find the oxidation numbers. But this method is a good one. There are specific uses of this method too. You can go to the theory note and check. When you need to find real oxidation numbers of, let's say, thiosulfate or some iron tetrathionate like ions, you need to draw these and find. Okay, but there is another method which we call as mathematical. That's some name I implemented. That mathematical method, you can do a small calculation and find an oxidation number also. That method is more suitable for this MCQ. Okay, so but this method is the one that gives you the proper idea about oxidation number. That's why I reminded you this one more time. Now let's go to the other method. Other method is telling what? Right? In that method, you have specific oxidation numbers. Okay, for example, oxygen, it is always, you can see, usually it is gaining 2 electrons, right? Partially or totally, gain 2 electrons. So generally, oxygen oxidation number is -2. There are exceptions. You can visit your note and see. There are exceptions. For example, hydrogen peroxide oxidation number of oxygen is -1. That is an exception. But generally, if you exclude those 2-3 possibilities, generally oxygen is -2. Okay, and then like that hydrogen is generally +1. Okay, so but others, let's say group 1 elements always +1, group 2 always +2. Those are fixed oxidation numbers. You will remind this under inorganic also again, because when you describe inorganic chemistry later, now we are finishing this block now these days. So group 1 and group 2 S block elements are having fixed oxidation numbers. But when you go to the P block, it changes, right? Some P block groups are there. They have variable oxidation number. Example, the group that belongs this carbon, group 14, right? It has a range of oxidation numbers from -4 to +4. Okay, so like that, it depends. But for group 1, group 2, and group 13, it's having +3. And fluorine is always having -1. It's the most electronegative element. No, nobody is going to gain electron from that one. It is the one who gains from everyone. Okay, so it's always minus 1. Can understand this? Okay, like that, there are fixed oxidation numbers. You can use this to find, and using this theory also, you can easily find oxidation number. Now let's do it for carbonate. Carbon is the element you don't, the element that you don't know the oxidation number. Let's label there its oxidation number as X. Then oxygen, you know the oxidation number, it is -2. So there are 3 oxygen atoms, -2 into 3. And this is the total of oxidation numbers of the atoms. And total will be equal to, like this says, to the charge, which is -2. Now if you simplify this one, you will get the oxidation number, X equal +4. It is easier. Can you understand now? Okay. So now if you apply this one to nitrite, right? Then X plus -2 into 2 equals to -1. So X minus 4 equal -1, X equal +3. Now if you improve this ability, and I know most of you have that ability right now, it's very good, I appreciate that, right? You can find the oxidation number just by looking at that. No need any calculation. Okay, so NO2 minus oxidation number is +3. Like that, if you continue to do that one for chromate, see, 4 oxygen atoms -8. And that goes to the other side, +8. And it's simplified with -2. Gives you the +6 oxidation number. See, it's very easy. And you had another ion in this question, SO32 minus. It is very similar to CO32 minus. It is having +4 oxidation number. Understood? So that's about oxidation number. This is the level I told you to understand. So now let's go and find our answer. Answer is answer 3. Answer is answer 3. So is that clear now? Is that clear? Oxidation number. You can now see to find oxidation number, you need electronegativity, dipole moment, Lewis structures. Okay. And after finding oxidation number, it is used for other purposes too. Remember, we used oxidation number for balancing redox equation. That's the main advantage. And then we used oxidation numbers to check the electronegativity trends. Remember? Huh? So like that. So if you don't know, let's say, how to draw the Lewis structure, you can't do any of those things I mentioned. That's where it gets interesting, right? That's why second lesson is hard for some students. Because if you didn't practice enough Lewis structures, then, like I explained here, you will get stuck at some point. Okay, so now let's go to the next question. Fourth one. Yeah, what is this theory? That just comes to your mind by looking at this. An electric bulb with power 400 joules per second glows for a certain time, emits 12% of the energy in the form of light. So it gives you so many data on it. Look at this other sentence. When the bulb glows for a certain time t, the light energy emitted. So light energy is just one part of the energy, only 12%. So that means 12% of the energy of this bulb is emitted as what? 12 into 10 to the power 20 photons, light energy. So if you find this energy of this total number of photons, you can calculate backward and find the total energy of the bulb. Let's say for example, E amount of energy is emitted as light. Then how do you find the total energy? E is equal to the 12%, right? Isn't it? So you divide that one by 12 and multiply by 100. Then you get the total energy released by the bulb. So if it is a bulb, you know what happens to the other energy, right? From O levels, you might have learned it. If you get a simple filament bulb, right? Only a fraction of its energy is released as light. Okay, other energy, other amount of energy is released as heat. You know that. Okay. Okay, so that isn't needed here. But anyway, just understand the whole picture, then it will easily come to you. Right, so they have given the wavelength of one photon. So using that wavelength, 331.3 nanometers, you can find the energy of one photon. So after finding energy of one photon, what you can do? You can find the total energy emitted by this amount of photons. Can you understand that one? So this is how it goes. Okay. So what is the theory part? I asked that question at the beginning. This theory part is quantum theory, right? Quantum theory. Okay. So it was proposed by Max Planck. He said that energy that we see in the nature is not continuous. It is kind of, we say, what's the word? We say quantized. Remember that word. We say energy is quantized. So it is broken into packets of energy. Okay, he called that one as quanta. But later Einstein explained it further, developed the theory further, and named it as photon. Okay, so these photons, okay, we call particles of energy. Photons can act as particles also. Right, so anyway, my point is, okay, so photons, you can find its energy using this equation, E equal h nu. So first they have given lambda. It is 331.3 nanometers. So let's convert that one into meters. 331.3 into 10 to the power minus 9 meters. Okay. And then use the formula and find energy of one photon. So how do we find the energy of one photon? Using E equal h nu. So if you don't know frequency, you can use this formula, hc over lambda. hc over lambda. So c is the speed of light, which is 3 into 10 to the power 8 meters per second. This is wavelength, which is 331.3 into 10 to the power minus 9 meters. Then after finding energy of one photon, you have to find the total energy, total light energy, by multiplying this value from 12 into 10 to the power 20 photons. But this is the total number of photons. And then go to the total energy. How do you go to the total energy? Because this energy is just 12%. This is just 12% of total energy. So how do we find the total energy? Divide this one by 12 and multiply by 100. Divide this one by 12 and multiply by 100. Okay. So that total energy, using that, you can go to the time. Remember the equation for power? Power equals work over time, or you can say energy over time. So you can find the time just by dividing this total energy by the power. They have given the value 400 or something. So that's how you come to the time. Okay, I noticed some of you have done this question well. And this is a good question. It's kind of one of the hardest question you can be given from this topic. Okay, it's not only asking the energy of one photon. No, it's not that. Okay, but something goes beyond that. You can see total energy, and then you have to find the total light energy, then that just 12%. Then you have to find the total energy that emitted as heat and light and everything. And then not only that, you have to go to the time. So interesting. So study this question really well. And that may be enough. And that may cover everything that can come from this topic. Okay, so if you remember the past papers, you will understand what I'm telling here. Okay, right now I'm going to show you the answer, how to get that one. So I have one prepared for you. Look at this one, Lama. Look at this one. Energy of one photon. You use this equal hc over lambda formula. Then you substitute. So when you do this one in a exam, you don't need to put units. But right now, let's write units and see, then you will understand whether you made a mistake. Let's say you forgot to convert nanometers into meters, you will not get a proper answer. And can you see in the green color right here, I kind of, this part, the simplification was rounded off. Now instead of 6.626, I use 6.6. For the MCQs, it is fine. And instead of 331, I use 3.3 because I can understand. It will be cancelled to 6.6. Like that, round it off. Then simplify power separately. Then finally, you will get energy of one photon as somewhere around 6 into 10 to the power minus 90. 6 into 10 to the power minus 90. Okay. And then the total energy of 10 to the power 20 photons. Okay, that is 720 joules. And that is just 12% of the energy. No? Then you divide again that one by 12 and multiply by 100. So you'll get 6,000 joules as the total energy. 6,000 joules. Okay, so then you can divide this one by 400, which is the power. Will give you 15 seconds as the time. See? Okay, so you can write down this answer and the one in the board that explained the procedure to get there. It's a good question. It's a very good question, Lamai. Okay, so trust me, study this one well, and this will be enough for the other questions. So if you did this well, you can be really happy about yourself. Okay, very good. That means you know up to the level we need. Okay, still if you got a wrong answer or if you didn't understand the method or anything, just take this as a chance and study it properly. Okay, give me a minute, Lama. Okay, now let's go to the next question. Question number 5. This is actually from your 2025 A-level past paper from MCQ. Look at the question. The correct order of increasing electronegativities of carbon in the chemical species CH2, Cl2, CF4, like that. Okay. Finding the answer of the question is really simple. Okay, you have to find the lowest electronegative carbon and the highest electronegative carbon. That's it. You don't need to arrange them in order. That's how they check the A-level question, right? So I'll explain the whole thing, how to find them in order. But remember, in exam, just finding higher and lower one is enough for this particular question, because the way they gave the answers, you can crack the one without finding the proper order. Okay, so now I'll anyway explain the proper order, because we can't expect that to happen always, no? Right. So what are the four compounds? What are the four compounds? CH4 is there. Then you have CH2Cl2. Then you have CH2F2. And then you have COF2. COF2. Yeah. So what is the theory? Electronegativity of carbon. Electronegativity of carbon. Isn't carbon having a fixed electronegativity? Huh? According to Pauling scale, we say carbon is having 2.5 as the electronegativity. You remember? Pauling scale assign values for the electronegativities. Fluorine 4.0, hydrogen 2.1, like that. I gave the numbers, right? But anyway, carbon, according to that scale, 2.5. Now that means carbon is having a fixed value, right? No, it's not. Okay, so when you compare one element with another element, you can use Pauling scale nicely. Like we did use that one when we discussed, remember, oxidation number question earlier. You know, oxygen was having high electronegativity than carbon. So how did we know that one? Oxygen 3.0, 3.5 electronegativity, carbon 2.5, according to Pauling scale. So we can say oxygen is more electronegative. But here in this question, it's not asking you to compare two elements. It is asking you to compare atoms, different atoms of same element. So that means, Namai, oxidation number is changing depending on the nature of that atom. Let's say here there are 4 carbon atoms. No, for all carbon atoms, you don't have the fixed same electronegativity. It will be different. Okay, so one of these 4 carbon atoms will have a higher electronegativity and the other one may have lower values. Can you understand? So then we need to find what are the factors that change the electronegativity of this carbon. So that change is actually not a very large change only. So now carbon was 2.5 no, according to Pauling scale. That doesn't become 3.5, 4.5 or something, right? Okay, so higher means it will become 2.501, like that. Lower means it will become 2.49, something like this. It's a little bit varying around 2.5. That's what the idea, okay? Right? So I hope you understood it well. So what are the factors affecting electronegativity? So when it is asking you to compare electronegativities of same element, so one theory just quickly should come to your mind. What is that? Scope, right? It was frequently discussed in our classes. Scope is percentage, charge, oxidation number, and peripheral atom electronegativity. So those 4 things are affecting the electronegativity of central atom or the atom we considered. Here it is carbon. Can you understand? So you need to think about scope. Its percentage, charge, oxidation number, peripheral atom electronegativity. So then we need to address those things here. No? Its percentage, charge, oxidation number, peripheral atom electronegativity. Those things we need to check. So when these factors are increasing, let's say this percentage of this carbon atom increases, what will happen? Electronegativity will increase. So as all these factors are increasing, what will happen to the electronegativity? It will also get increased. Understood? Okay, so how do we check S percentage? What is this S percentage? I'm going to explain that too. Right? So let's go to the Lewis structure of these compounds. I'm selecting 2 here. So first one is CH4. CH4 Lewis structure is like this. And then the other one I'm selecting is COF2. Okay, COF2 Lewis structure is this one. You have to put lone pairs if you want to say it as Lewis structures, or you can, without lone pairs, you can say bond structure. Okay, bond structure. It's representing bonds. That also enough for this question. But anyway, since I said Lewis, now this is the Lewis structure with the lone pairs. With the lone, oh, sorry, there's no lone pair here, only 2 lone pairs. Okay. Now anyway, now you can see there's a difference between 2 carbon atoms. Now here, it is having 4 single bonds. But this one here is having only 2 single bonds and 1 double bond. So 1 double bond means you have a sigma bond and a phi bond. Sigma bond and a 5 bond. Double bond means what? Sigma bond and a 5 bond. Sigma bond and 5 bond. Sigma bond and 5 bond. Double bond. Okay, so if you just explain further, sigma bonds and 5 bonds, right? 5 bonds are made by overlapping of lateral overlapping of unhybridized p orbitals. Lateral overlapping of unhybridized p orbitals. Understand? So then if you take the carbon electronic configuration, it is 1s2, 2s2, 2p2. Okay, so if you take the valence energy level, this is the valence energy level, valence or the last energy level. So it has in s orbital, I'll draw like this, you have 2 electrons, and there are 3 dumbbell shaped p orbitals, and in each orbital you have 1 electron, and this is an empty orbital. So according to Hund's rule, you have to fill electrons like this. If you listen to my explanations from the beginning, you will remember Hund's rule. I explained it earlier. Now, if you further supply energy, let's say when this become excited, okay, so this electron jump to the empty orbital. Now it will come like this. So we say this is the excited state. And when it comes to the excited state, it will undergo something called what? Hybridization. When I'm explaining drawing the diagrams like this, you should remember this thing, hybridization. So here, this particular carbon will undergo sp2 hybridization. So you can see, I didn't mark one orbital. This orbital I left. Why? Because I left this one to make what? To make 5 bond. Because it need to make a 5 bond. So to make 5 bond, you have unhybridized p orbit. Okay, so when it undergoes sp2 hybridization, you will have, that means simply you mix these 3 orbitals and make 3 new orbitals. So those 3 new orbitals will look like this, same shape, same size, okay, but different orientations. Orientation will be what? Trigonal plane, 120 angle to each other. Understood? So then perpendicular to that one, you have your unhybridized p orbital like this. Okay, unhybridized p orbital. So if you draw these 120 angle orbitals in this way, let's say this is the triangle, trigonal plane. Let's say this is perpendicular to the board, this plane, and your p orbital is perpendicular to that plane. Understood? This is the one that forms a 5 bond later. And these are the one who's forming single bonds, sigma bonds. There are 3 single bonds. Can you now understand how this thing comes? Hybridization quickly. And about this carbon, if you say, if this carbon, when it is there like this excited state, since it don't need to make any 5 bond, right? It will undergo what? sp3 hybridization. That means all 4 orbitals, one s orbital and 3 p orbitals will undergo hybridization and make 4 new orbitals. 4 new orbitals. Understand? 4 new orbitals will be formed. Those 4 orbitals will arrange in tetrahedral electron pair geometry. Understood? sp3, just now sp3, that is enough. I'll explain tetrahedral and everything in another question. Right, now listen. Now it is sp2 carbon. This carbon is sp2. That's the final thing. So then what is the S percentage? Simply, what is S percentage? Out of the 3 orbitals here, sp3 means S and 2p's, no? So there are 3 orbitals. Okay? Out of the 3 orbitals, 1 is S. So here 1/3 is S. 1/3 is S. So 1/3 as a percentage is what? You just multiply it by 100%. What do you get? 100 over 3, 33.33 here. 33.33. This is the S percentage. Now can you understand what is S percentage? Now see, to get this question right, you need to know about the Lewis structure. Right? You need to know about the hybridization. And not only that, S percentage. Huh? Is that clear? Then what is the S percentage here? SP3. Think about that one. Now let's say there's someone who don't understand hybridization earlier. But from the discussion I did now, he or she got a little idea. Now should try to get the hybridization of this one along. So out of the 4 orbitals, there are 4 orbitals, no? S and 3p's. P, P, P and S, 4 orbitals. Out of the 4 orbitals, one is S. So as a percentage, 1/4, no? 1/4 into 100, but 25%. To get that one. You get that one. Here, you have S orbital and 3p orbitals, no? Before hybridization. Okay, so sp3. So 25% S character is there. So this S character will affect the length of the hybridized orbital, size of the hybridized orbital. Okay, it will affect shape also. So now, for example, sp3 hybrid orbitals are longer, okay, than sp2 or sp orbitals. Sp orbitals are very short. Okay, because S character, when S character is higher, orbital length is lower. That's why in here, sp2 hybridization, 33.3 S character is there. So that orbital is a shorter one. Okay, now I'm going to tell you how it is related to the electronegativity. When the orbital is shorter, what will happen? If, let's say, if you're having a short orbitals, that means electrons are very closer to the central atom. Then it is very easier for the central atom to attract those electrons. You get my point? It is very easy to central atom to attract those electrons. So electronegativity will be what? Will be higher. Get the idea? That's why when S percentage is higher, electronegativity becomes higher. Okay, right? So then the most electronegative carbon is this carbon from this answer question. Okay. So 33.3 S character. Short orbitals, more ability to attract the electrons. Understood? So don't mind about the others around the carbon. We are just thinking about the ability. We don't discuss whether it has actually attracted electrons. Okay? It's not the thing. We discuss the ability of carbon. Ability is high. Now you can see carbon is bonded to oxygen and fluorine, which are more electronegative atoms than carbon. Okay, so then when you go to the actual situation, carbon has lost electrons here. But what we are discussing here is not the actual thing. What we are discussing here is the ability. Ability of carbon to attract electron is high. Ability is something else on it. Understand? Ability to attract is high. I hope it is very much clear to you. Okay, so like that, if you get the structures of other two, CH2Cl2, CH2F2, they are kind of similar tetrahedral structures. Cl, Cl, F, F. So they also have what? 25% S character. So the one with the highest S character is this one. So this is the most electronegative carbon. So if you arrange them in order, COF2 will be the most electronegative one. Understood? So if you check the answers, there are only 2 answers that is having COF2 as the highest value. Then you have to select the lowest one. See, because the first answer and the second answer, lowest electronegative one is different. That's why I said you don't need the full explanation to get the answer. But anyway, we are doing it here because I said at the beginning, my target is explaining them deeply. Okay, so when you come in the next new year, 2026, that is your year, Lama. Okay, in this year, next year, Hari, Now we are finishing the 2025. It's December 27th today. Right? When you go to the 2026 year, that is your year. You may write A levels in 27. Right? But everything you learn, okay, your maximum effort you should give in this new year. So my target is when you are coming the new year, our first class, okay, you must go through these theories well. Okay, at least you have to fix your problems. Understand? That's why I'm discussing this one today. Okay, this is supposed to be a holiday for us, but anyway, okay, your education is far more important than anything, right? Because if you learn properly only, then as teachers, we also have a good future. Understood? Okay, so do it well. Right? You all have a very good potential. I noticed that. Okay, so generally, when, like I'm telling always, right? When there are 70,000, 60,000 students write A level chemistry, right? Only, let's say 10%, 6,000, 7,000 gets A passes, right? So it can't happen to our class. Let's say if our class has 100 students, then not only 10 students should get A's, it's no different from the general sample, right? If there are 100 students, you should get, let's say, at least 50 students get A's. Then our class, our teaching methods and everything, exam procedures and our class plans, they all are perfect, isn't it? So that happened in earlier years, 2022, 2023, 4, 5, right? I taught small batches, but still the pass percentage and A percentage is a very high one related to the general sample. So I need to do that one in 2026 and 2027 batches also. Understood? So 2026, I have no fear. They are really good. They are going their path, right? But 2027, you kids, right, have a lot to improve. Okay, that's why we are doing this one. So understand it. Okay, understand this one. So let's do it. Okay, so now how do we check the other points? Charge, oxidation number. They're very simple. They're very simple. Now, what I noticed in some students, when we go to the charge, so they try to look at the overall charge. It's not the overall charge. Charge, what we are mentioning here, charge of carbon. Charge of carbon, just simply write it. So, do we see any charge in the carbon? No. And you don't need to check this one. Why? Because we already know that is the highest. So no point of checking other points. So don't check other points, okay? Otherwise you will get confused. Right? Once you, this is a priority order. I forgot to mention. This is a priority order. That's why you have to remember exactly in this way. If you have same S percentages only, you go to the next step. That means you go to check the charge. If you are having same charges like this, what you should check now? Oxidation number, which you learned earlier. Okay, so simply, what do? We mark dipole moments and check that. So what is the dipole moment? Here, carbon is more electronegative in Pauling scale. So it actually attracts 4 electrons. So -4 is the oxidation number. Partially gain 4 electrons. We explained that today. And here it's both losing and gaining is there. Carbon is more electronegative than hydrogen, only. But chlorine is more electronegative than carbon. So here carbon losing 2 electrons. So loss 2, gain 2. Oxidation number is 0. Do you understand that one? Loss 2, gain 2. Here what is the oxidation number? Same happens. Loss 2, gain 2. Oxidation number is 0. So now you know to compare between the middle two, you need to go to the next level. But you know this is the least electronegative carbon. Okay, so in your order, it should be CH4. That's why I said earlier. It's very easy to find the answer. There's only one answer, I think. Answer 1. Yeah. Okay, now, but let's not stop there and let's discuss about the other two also, because it's also there for our syllabus. Now, we need to go to the last point. which is peripheral atom electronegativity. So which one is having higher peripheral atom electronegative one? Okay, so you can see hydrogen is same. So then you have to think about whether it is chlorine or fluorine. Which one is more electronegative? Fluorine. Okay, so then this is having higher electronegativity and this is having lower electronegative carbon. Okay, so can you understand what is happening there? When peripheral atom becomes more electronegative, this delta charge becomes more and more higher. When peripheral atom is less electronegative, then this delta charge is plus, but it is not that positive. If it is having a higher charge, it is having higher ability to attract electrons. So it's kind of indirectly related to the first point. Oxidation, second point. So oxidation number is also related to the second point. Understood? You have to watch the theory discussion of this lesson. I explain why these 3 points comes after this character. That also I explained. They are never going to ask that in A-level exam, right? But I gave you a proper 100% clear idea. I don't know whether others are teaching that one, but you should know this. Can easy. Right? Getting the clear idea at your head is enough, right? So then understand here, when peripheral atom is more electronegative, it induces more charge, more plus charge on carbon. That facilitate to attract more electrons towards carbon. Attract more ability to attract. Okay, it's not actually attracting, but this carbon here has a higher ability to attract. Understood? So that's how you compare electronegativities. Okay, that's how you compare electronegativities. Okay, so then what is the more electronegative one out of these two? CH2, F2. And here CH2, Cl2. Okay, so that's the full review about the MCQ. Right, a good one, right, a lengthy one. Okay, if you are struggling here with these theories, you should do that. So answer is answer 1. Okay, so now let's go to the next question. That is also from our 2025 A-level paper. Kind of a easy one. I'll explain it quickly. It's simply asking about atomic number, mass number, proton, number of protons, neutron, electron. They are checking your knowledge here. How did they make this to A-level standard? Because generally, number of proton, neutron questions are asked in O levels. How did they make it to A-level standards? How? By giving so much data, so much unknown things. Now, not only A or B, here you have A, B, C, D, E, 5 variables, 5 different things to find. That's how they make it difficult, but it's not difficult in the sense, right? But it's kind of better than O-level questions. Okay, now let's see how to find it. So there's an important statement. Y is heavier than X. That means what? Y is heavier than X. That means a mass number of Y is greater than X. Greater than X. That's the idea. Okay. So then if you check the mass numbers, go and check this one. If you check the mass numbers of Y, which is E should be greater than D. So there's only one answer, which is E is lesser than D. This one. So then answer 4 is wrong. Understood that one? E should be, therefore, E should be greater than D. And fourth answer is wrong. You are eliminating the fourth answer. Okay, eliminating the fourth answer. And then check this again. Now you can see, if you check again, you will see the number of electrons of X is given. A number of protons of Y is given. Okay. So what is the relationship between protons and electrons? Protons and electrons. The number of protons and electrons of a neutral atom must be same. That's why it is neutral. Number of protons and electrons should be same. Okay. So the next point is for a neutral atom, number of protons is equal to number of electrons. So then for X and for Y, they have given, for X they have given, let's check again. For X they have given number of electrons. Okay, number of electrons is 6. Therefore, protons is also should be 6. And for the Y, they have given protons, which is 6. Then electrons also must be 6. Can you understand that? So then you can easily decide the value of A equal to 6 and value of what is that, C, no? Value of C equal to 6. Then check whether any answer is there are having different numbers. Then you can see first one is wrong. Second one, okay. Third one, okay. And look at the fifth one. Fifth one is also wrong. You could eliminate another 2 answers. Okay, now if you check carefully, okay, if they are having same number of protons, that means it is same element, no? Now same element, different atoms, different mass numbers are there. Same element and different mass numbers. So what are these called? These are called what? Isotopes. So these are isotopes of exactly carbon. Because atomic number 6 is for carbon. Isotopes of carbon. So you have here C613, which is X, and C614 for Y. Okay, so you know different mass numbers are due to different number of neutrons. So here, then this Y and X should have different number of neutrons. So you can simply subtract number of protons from the mass number. So if you subtract 6 from 13, you get 7. You get here 8. Okay, so if you check that small point, you will isolate the answer. It's an easy question, kind of the easiest question in the 2025 A-level paper. But yet, within the time and within the exam threats, some student might get wrong. Okay? So anyway, answer is answer 3. You can see clearly. For the B means the the number of neutrons of Y should be 8. Okay, anyway, answer 2 can't happen. Why? Because if they are isotopes, their number of neutrons must be different, no? Okay, X is having 2 neutrons, 7 neutrons. And according to the answer 2, Y also having 7 neutrons. It is not possible. So in that way also you can select. It's easier. That's what I want to say. Right, I hope it is clear. Let's go to the next question. Okay, now this one is from gases. There was a very similar past paper question came, I remember in 2021 or 2. Okay, a very similar one, but this is kind of advanced than that. A small problem was there with the question. I corrected that during the paper writing. You need the you need the mass numbers of helium and neon. Okay, you need the mass numbers of helium and neon. So what is the mass number of helium? Helium mass number is 4. Neon mass number is 20. Or you can say relative atomic mass. This is a proper term. Huh? Relative atomic mass of helium is uh, relative atomic mass of helium is 4 and neon it is 20. You need this one to do the question. Okay, now look at the question. A closed rigid container at room temperature contains helium and neon gases. Their mass ratio is 1:2. Now they are not equal masses. Okay, but the level question that I'm telling you, it was given as equal masses. Okay, equal masses. But this one, there's a mass ratio. So when you see such a ratio, it's good to put it in kind of in algebraic terms. Okay, so for example, you can say if the mass of helium is m, okay, you can say start by telling that one. That's easy. So then the mass of helium, let's say it is m, then mass of neon should be what? 2m. Okay, because their ratio, helium to neon mass ratio is 1:2. That means you have more more neon mass. Understood that? Then the total pressure of the container is 1.4 P. They are asking the partial pressure of helium. Partial pressure of helium. Now, in this container, you have both helium and neon gases. So when they collide on the wall, when these gas particles are colliding the wall, both gases are generating its own pressure. Okay, so pressure is generated by, according to the gaseous state lesson, pressure is generated by the collisions of gas particles, gas molecules on the wall of the container, sides of the wall, right? So then that's how it that's how it generate the pressure. Okay, so here two gases are there. So both gases are giving its own pressure, P helium and P neon. So we call these as partial pressures. And the addition of these two pressures gives you the total pressure, which is given by the Dalton's law of partial pressure. So according to that one, P total is what? P helium and P neon. Understood? But knowing only this equation is not helpful for us. You need one more thing. You just remember Dalton theory, which I discussed with you in gaseous state lesson. You will realize we can take a step forward and derive another equation for the Dalton's law using, applying, I'll tell you the method, by applying PV equal nRT for one gas and applying PV equal nRT for the total mixture. We can get a new equation. Okay, so that is the one we have used here. Partial pressure of helium is equal to mole fraction of helium into P total. Remember this equation is very useful in other lessons too. Okay, so what is this? This is mole fraction. So mole fraction you learn in chemical calculation. So what is mole fraction? Moles of helium over total moles. Understood? Then we can rewrite this one again. Moles of helium, total moles means moles of helium plus moles of neon into total pressure. Okay, so this is the equation we have to use. Understood? To get the moles of helium and neon, we are going to use the masses. So what's the moles of helium? You have to divide the mass, which is m, by the molar mass of helium, which is 4 gram per mole. You will end up with 0.25 m. And the moles of neon, 2m over 20, which is 0.10 m. Sorry, yeah, 0.10 m. Then apply them here. Apply them here. 0.25. 0.25 plus 0.1 times the total pressure was 1.4 p. This gives you 0.25 over 0.35, 35. Okay? Into 1.4. Now you can see this divisible. If you simplify it, you can divide by 7.2. This will become 0.5. Then if you cut this one, it will become 0.05. No, not 0.05. It will become 0.05 here. Then if you cut this one, this will become 5. Okay, and 5 into 0.2, 1. So the answer is P. Can you understand the method? So the same thing I can show you. I noted that in the discussion too. Here you can see. Answer is answer 1. Answer is answer 1. Okay, Lama? Answer is answer 1. That's the answer for the 7th question. So about partial pressure, this comes under gas laws. Ne? Gas laws. In gaseous state lesson, we discussed that one within 5 days. We divide nicely the lesson into 5 topics. And actually the theory was completed in 4 days. And the 5th day was for the practicals. You can't ignore the practicals of these lessons. They are very important. So again, study that part one more time. If you need the recordings, you can ask. Yeah, now let's try the question number 8. There are 5 statements. It's asking which one is incorrect. So I'm going to explain it fully, one by one. Yes, that's my aim today, not the number of questions, the quality of the discussion we do today. Okay. Right, look at the first one. Electron pair geometries of these 3 ions, Xe, OF2. Then you have XeOF4, right? And then you have SF6. These are the 3 ions. They're asking which one is incorrect. Okay, so we're going to explain the first statement. They are telling electron pair geometries of these 3 ions are the same. Okay, now let's check whether this statement is true. Now for that, what we need? We need their electron pair geometries. Now, for earlier questions that we discussed today, I directly got the Lewis structures without the Lewis method. So I was saving the Lewis method reminding for this question. So I'll explain you the Lewis method, okay, for this particular question. Okay, just kind of reminding, okay, see whether what is you're missing. So how do we draw the Lewis structure of a molecule like this? Okay, first, you need the skeleton structure. Skeleton structure. That means you need to generally show how the bonds are there. You need to find a central atom and then put the other atoms around there. So how do we decide the central atom? Central atom is the least electronegative atom. So you have xenon, oxygen, and fluorine. So no doubt xenon should be the least electronegative atom because you learn oxygen and fluorine to be the higher electronegative atom. Fluorine is the highest, right? So then xenon is nowhere in that list now. The one we remember. In that list also, xenon is not there. It's actually noble gas. Okay, kind of very low electronegativity is there. So actually we don't discuss electronegativity for the noble gases. It has a value, but kind of not relevant. Okay, because anyway, only xenon is going to make bonds like the xenon and radon. Okay, others don't make bonds. So anyway, my point is xenon is least electronegative. You can understand that. Okay. Then how do we take the other steps? So according to the Lewis method, you need to find their number of total valence electrons, because at the end, in the Lewis structure, we are representing how those electrons are distributed. Okay, so don't always take them as rules only. Otherwise, you are not learning it. Just know why we are doing that one also. Okay, so central atom, okay, and understand. And why do we count the total number of valence electrons? Because the reason we're going to show how those electrons are distributed. That's the idea, right? So now find the total valence electrons. From xenon, it is an element in group 18. So it has 8 valence electrons. And fluorine, it has 7 valence electrons, and there are 2 fluorine atoms. So 7 into 2, 14 electrons. And from oxygen, you have 6 valence electrons. 6 valence electrons. So altogether, you have how much? 28 valence electrons. So from those 28 valence electrons, you can see we already have represented some electrons in that skeleton structure. So how many electrons? We already have represented 6 electrons, because each dash here represents 2 bonded electrons. Okay, so 6 electrons are represented. So you are subtracting that from this total electrons. So you get 22 electrons. 22 electrons, and then you are going to convert that 22 electrons into electron pairs by dividing it from 2. So you get 11 electron pairs. So why do we convert them into pairs? Because usually they are occupied in orbitals. That's why I said earlier. See, everything we are discussing today is nicely linked. I thought about this one for hours and how to do the discussion today. So you can see it is related. So these electron pairs are there in orbitals, because you know in an orbital you can keep only 2 electrons, right? So it's related. And these 11 electron pairs, you are going to distribute them now, starting from the most electronegative atom here, fluorine. Okay, so until its octet is completed, you are going to apply electrons. Okay, so that means to complete the octet, because that's the stable configuration, so everything happens to gain stability. You put 6 and you put another 3 for oxygen. So 9 electrons are distributed, another 2 is waiting. So that is applied for the xenon atom. Okay, then you check, whether the octet of central atom is also completed. You can see it's exceeded actually. So you don't going to erase anything only, just keep it. First of all, you have to check. There are some elements when we draw the Lewis structure, central atom octet is not complete. Then what do? We make a 5 bond, we make a double bond to complete it. But right now here we don't need to do that one. Okay, because central atom octet is complete. That's the next step. And after the final step is checking their formal charges. So here fluorine is having 7 electrons. He brought 7 electrons when it comes to make the bond. Right now it has 6 electrons as lone pairs, and there's 1 electron from the bond. Because this is sharing of electron, actually 1 electron is belonging to the fluorine. So he brought 7 and he has 7 right now. 1, 2, 3, 4, 5, 6, and another electron from the bond. Okay, and saying no charge for the fluorine, no charge for the other fluorine, but for this oxygen, you'll have a -1 charge. Why? He brought only 6 electrons, but right now, like fluorine, it is having 7 electrons. He has 1 more electron, so minus charge. Then check out for xenon. He brought 8 electrons, but now see how much he has. 1, 2, 3, 4, 5, 6, 7. 7 electrons. So it's 1 missing. Okay, so that's the formal charges. Now, if you can violate the octet rule, you can make more bonds. So now xenon is already violating octet rule because it's a lower period element. I mean, it's there in the, I think, 5th or 6th period, right? So it can make more bonds. So now to minimize the charges, let's make a double bond. And the final structure for xenon is going to be something like this. This is the final Lewis structure. Is that clear? Now you can repeat that thing to the other molecules also. Okay, so now one of my aims was here to remind you the Lewis method in this video. I hope it is clear to you now. And with more practice, you have to first practice with this method. Enough molecules you have to draw, take days, weeks, it's fine. And after doing a great deal of drawing structures, right? And you will develop a sense that it's kind of repeatable. You will see always when fluorine comes as the peripheral atom, it's always the peripheral atom. It's never going to be central atom, fluorine. Okay. When fluorine is there, it always makes a single bond. When oxygen is there, okay, it either makes single bonds or double bonds. So if it is having no charge, then it must make a double bond like here. You can use that at practice. Okay. So then you will realize here, xenon is having 8 electrons. From that 8 electrons, 2 electrons will be reserved to make a double bond with oxygen. And another 4 electrons from that will be reserved to make 4 single bonds with fluorine. Understood? So then how many electrons will remain? Only 2 electrons. So that 2 electron means 1 lone pair. Okay. So around xenon, now if you try to draw the structure, there will be a double bond. There will be 4 fluorine atoms bonded like that, and there will be only 1 lone pair. Can you understand? So without any effort, I mean, within a small time, you can draw the Lewis structure. So this is a result of practice learn. Don't straight away try to do this one. That's my advice. So practice it. Draw enough structures. It's fine. Depends on the level you grasp this one. It's fine. Use this. At some point, you will be able to draw like this by thinking. Okay. So then if you want the Lewis structure, you have to put lone pairs. For this question, lone pairs is not necessary, but anyway, this is the Lewis structure. And if you continue to do that one for the flow, this molecule, and this is what you will get. Sulfur is violating octet rule. Okay. Right. And the next one. So how do we get this one? If you remind it again, find the valence electrons of xenon and check whether oxygen is making a double bond or a single bond. If it is having no charge, it is making a double bond, right? And then subtract 2 electrons for that one. And fluorine always makes single bonds, no? So there are 4, no? So subtract 4 electrons from this. Then you will be left with 2 electrons of xenon, which is acting as a lone pair. So my advice is this is not a method learn. It's not a method. This is purely practice. Okay, so don't try to study this one. Don't try to remember this one. It's no point. Because without this practice, if you try to remember the short method, it's not going to work 100%. Okay, so just use this method. Practice enough. Okay, no problem. Take your time. Because your A levels are there in 2027. Take your time and use the proper method. At some point, you will realize this for yourself. Okay, so that's the advice on it. Don't memorize this on it. Just memorize, because I know some students are now doing this way. It's fine, good. Because how can they do this one properly? Because they practice enough questions using the proper method. That's why. So if you are someone who's looking to jump into the short method, don't do it. Okay? not going to work. Waste of time. So use the proper method and do. I hope you understand what I'm telling you. At some point, you will do this. Okay, don't worry. Don't worry. Just follow the proper method until you get enough practice, then come to this. Okay, right. Now is Lewis structures is not the problem they're asking here. What are they asking? They are asking about what the electron pair geometry. So now the next theory point. What is that? VSEPR theory. In short, we call VSEPR theory, right? VSEPR. It's not truly written like VSEPR, right? But VSEPR theory. Valence shell, electron pair, repulsion theory. Valence shell, electron pair, repulsion theory. VSEPRT for short. So it simply gives you the idea what happens. I did a very good explanations regarding this one in earlier paper discussions. You can go and visit that one and can watch the recording of the lesson or just go to the theory note. That is enough. No need to watch recording for everything. Right? You have a nice note. And what is valence shell? Valence shell means this round xenon. This is the xenon valence shell. You can see these electrons are there. Valence shell electron pairs. This lone pair, bond pair are there. And it says repulsion. That's the important thing. They repelling from each other. That should happen, no? Why? Because always electrons are negative, same charge. So, similar charges are repelled from each other. Remember, in O levels, and before that even, positive repel from each other, negative repel from each other. So, similar charges are repelling from each other. Only positive, negative are attracted. So, there's nothing positive, negative. Electron pairs are negative. So, there is a lone pair, 2 negative electrons. Here's a bond pair, 2 negative electrons. So that means they should repel from each other. That's the idea. So according to this theory, it says, depending on the number of those electron pairs, or simply we say repulsion units, okay, it will assume a certain geometry. Let's say if there are 2 repulsion units, the geometry, the stable geometry is this one, having them 180-degree angle to each other. So then the repulsion can be minimized. Get the idea? Repulsion can be minimized. So electron pair geometry. Very simple. Okay. Then if you are having 3 repulsion units, what will happen? What is the suitable way of arranging them? 120-degree angle to each other. See? The highest gap. But when it comes to 4 repulsion unit, don't say 90. If you're following the method, you might divide 360 by 4 and say, okay, 90. Angle. No, it's wrong. Why? Because we are not living in a 2D world, we are living in a 3D world. So, why don't you think about the other dimension? You have a depth also. Not only length and breadth. You have height, depth also. So then, you can think about the 3-dimensionally. So if you go to the 3-dimensional space for the 4 repulsion units, if you're having 4 repulsion units, you can say 2 repulsion units are in front of the board and 1 repulsion unit behind the board and another repulsion unit along the board. So when you say that one, you will have 109.5-degree angle. It's a greater value than 90. It's the most stable arrangement for the 4 repulsion units. Why? It's having more angle. More angle means more distance away. Less repulsion. Get the idea? So then you can say 2 bonds, 2 repulsion units are behind the plane and 1 repulsion unit in front of the plane also. Because if you go to the other side of this wall, you will see that, no? Can understand, right? So anyway, they are not in the same plane. Understand? Tetrahedral not in the same plane. Remember that point. Really important for the next question. Okay, so like that, it continues. What are the repulsion? What are the geometries you have? Linear, trigonal plane, tetrahedral. Then there are 5 repulsion units. You have trigonal bipyramidal. Okay, trigonal bipyramidal. And then you have octahedral, 6 repulsion units. These are the electron pair geometries, they are for our syllabus. These are the electron pair geometries, they are for our syllabus. Linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. Remember this only. Then check this. Check this. So what is a repulsion unit? Repulsion unit is either a lone pair or a bond pair. So now if you check this atom, this xenon, yeah, let's take this one. You have 2 lone pairs. Then how many bond pairs? Some students are mistakenly say 4 bond pairs. It's wrong. Here you have 1, 2, and this taken as a single repulsion unit. Don't say 2 units here. Okay, double bond, triple bond, still a bond, right? So a bond pair. Because double bond, you have 2 sigma and phi, but they can't repel from each other. Because they form between the same 2 atoms. How they can repel from each other? Just think there are 2 lines between certain 2 atoms, and can they repel from each other? Then the above atom should split. It will not happen. It's done a simple theory, right? So then the double bond or a triple bond still a 1 unit. Remember that one. 1 unit. So there are how many units? 5 repulsion units. Then electron pair geometry should be trigonal bipyramidal. Then check the other one. Here you have 1, 2, 3, 4, 5, and 6 units. Octahedral. See, different. This is octa. This is also octa. See, 6 bonds. And this is trigonal bipyramidal. So, will that statement be correct? Check that statement again. Check that statement again. The electron pair geometries of these 3 are the same. So, it is the incorrect statement. The very first statements, you are lucky, right? You figure out that. Right? First statement is wrong. So, their electron pair geometries are different. Different. Understood? First molecule is a trigonal bipyramidal one. The last 2 are octahedral. So, that is our answer. So, all other 4 statements are correct. We'll discuss them in a minute. But see, this is your answer, first one. First one. Is that clear? Understood well? First one is the answer. Now, what is this trigonal bipyramidal? What is this octahedral? You may have doubts, no? Trigonal bipyramidal, I explained tetrahedral in the board, no? Trigonal bipyramidal means, Lamai, in the plane, you have 3 bonds. To make you understand they are in the plane, we draw these dotted lines. So trigonal bipyramidal, you have a triangularly arranged in 120 angle to each other, 3 repulsion units. And other 2 repulsion units are perpendicular to this triangle. Understood? Other 2 repulsion units are perpendicular to this one. Now, this is how 5 repulsion units are arranging. Then why it is called trigonal bipyramidal? Okay, so let's connect them. Then you will get a trigonal pyramid, no? Triangular base is there, and there is a pyramid, trigonal pyramid, and there is another pyramid just under that one. That's why it is called trigonal bipyramid. In your schools, there are models for this one. You can touch and understand. Or just go to the YouTube and check a video. You can nicely rotate and see. In our class, we did that one. Right? You can watch the recording. But my point is anyway, right? Trigonal bipyramidal means there are 2 triangular base pyramids attached to each other. Okay, and what is octahedral? Octahedral means you have 4 repulsion units in the plane. Now they are having 90-degree angle to each other. And there are 2 repulsion units which are perpendicular to that. That is octahedral. Understood? So, Your 5 electron pair geometries are linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. Okay, octahedral. Then you have something called shape. Okay, so molecular geometry, or we say shape simply. Shape. Shape is different from the electron pair geometry when you have lone pairs. Now, for example, earlier SF6 was there. SF6, there were no lone pairs. So, electron pair geometry and the shape both are octahedral. But take to this one, SF4O, SF4O, or you can say XEOF4 simply. Huh? And here you have a lone pair. So then this lone pair, when you check the actual orientations, you will not see the lone pair. The effect is there. That's why this was octahedral, but you will not see this. So if you connect what you see, okay, so you will get a square base pyramid. So we call this shape of this molecule is square pyramidal. So let's say this also was a lone pair. Then you will see square planar. Can understand easy. Okay, so the shape of this one is square plane. You can add that one to your discussion. And what is the shape of this molecule? This was of trigonal bipyramidal originally. And there were two lone pairs. So those two lone pairs are coming to the plane. Coming to the planes. Let's say these two become lone pairs. So what you will see? You will see, when you check, you will see something like this. The bond arrangement. So it is T-shape. Remember, T-shape. Study that one well and remind that one. Easy. Easy. Okay. So first option is wrong. Okay, now let's go to the next statement. I'm going to explain one by one. Basically, when we finish the discussion here, we're going to discuss bond length, bond angle. So basically, the whole second lesson will be revised. Right? I'm not sure I won't be able to finish the whole discussion right now. But anyway, I'm going to discuss like this by taking few days, right? So let's finish the MCQ discussion like this in details. So any student at any level can come to the level that I am expecting. Okay, so we have to do that one, mind it. Right, now let's check the other two statements about bond angle and bond length. So they are supposed to be correct. Let's review them. So first one is about bond length. Bond length. So they are checking bond length of 3 ions and molecules. So first one is carbon dioxide. Then you have oxalate ion. Then you have carbonate ion. These three. So what is this bond length? Bond length, if you just, if I tell you the theory points quickly, bond length is affected by several factors. Bond length is affected by several factors. And yeah, it depends on the length of the orbital you check. Let's say the orbital is, let's say the bond length is affected by this, let's say HF, HCl, HBr, like that, bond length increases. Why? Because fluorine is in the second period, it is having 2p orbitals, right? So 2p 1s overlap. Here it is in the third period, so 3p. If you check the configuration of chlorine, you will realize. So you are ending the configuration with 3p5. That means it is having 3p orbitals for the bonding. So 3p orbitals are long, because you know when you go forward, go downward the group, energy levels are increasing, atomic radius is increasing. So Br is 4p, like that. So bond length, what would happen to the bond length? it will increase. Bond length will increase. Understand? Bond length is increased. Bond length is increased. Right? And there is one reason to compare the bond length. But here it will not be applied, because the same elements, carbon, oxygen. So that theory can't be applied. Let's say it is carbon, sulfur or something, then you can think about that rule. So that means there are other factors affecting about the bond length. So one factor is the hybridization or the number of bonds. Let's stand to that one, number of bonds. And number of bonds is also causing to change the bond length. Let's say there is a single bond between X and Y. It is longer than the double bond between X and Y. And it is longer than the triple bond between X and Y. Can you get the idea? So when you have more number of bonds, the bond length becomes shorter. Bond length becomes shorter. They are very likely to move towards each other. They approximate towards each other. Understood? And that is partially explained by explained by the other point, hybridization also. Okay, hybridization also. Hybridization means now, if they are making a double bond, it must be sp2. It should be sp2 hybridization according to our syllabus. And if it is making a triple bond, it should be sp hybridization. So sp orbitals, I explained you, they are very short. sp3, sp2, sp. So it has less s character. That means they are very long, more p character. This should be little shorter, and this is very short. This has more s character, more spherical, you can see. Can you understand? So if it depends on the hybrid orbital also. So that's why triple bonds are shorter. Depends on the number of bonds and the length of the hybrid orbital. Can get the idea, right? Okay, so now if you go and check these three things, these three species given, carbon dioxide Lewis structure is something, the bond structure is something like this. It has a two double bond. It has two double bonds. Okay. And oxalate, something like this. So when you draw the Lewis structure of oxalate, you will realize you have other options also. And carbonate also the same. When you draw the carbonate Lewis structure, you will realize there are other options. Other options to make the double. Okay, so like that, the other options here are called resonance structures. Okay, so let me connect that one to our discussion here. So now the thing is, carbon dioxide is, you can consider this is the carbon dioxide molecule. But when it comes to oxalate and carbon dioxide, carbonate, you can't tell this is the real carbonate, this is the real oxalate. No, it's wrong. Understand? Because this is not the real structure, because like you said, like we understand, real, when you draw the Lewis structure, you will see there are other possibilities. So that means you can draw it in other ways also. Other ways means like this. By this, not only this carbon oxygen bond, this carbon oxygen bond can also be a double bond. And this one is also can be a double bond. See? So there are three structures. So these structures are called as what? Resonance structures. So here I just got the bonds. I didn't put the lone pairs. If you put the lone pairs, then they will be proper resonance structures. Okay, so actually, Lamai, real carbonate is none of these three, but a combination. But a hybrid, that's the word. A hybrid of these three resonance structures. So real carbonate is a combination, a hybrid of these three structures. So how do we draw that one? So for real carbonate, it will have single bonds, because all of these structures are having that single bond. But double bond, can you see it is distributed, no? Between the three oxygen atoms. So we mark that one like this. Double bond is distributed. So we call it as partial pi bonds. Remember, partial pi bonds. So real carbonate will be something like this. This is the hybrid. Okay, so theoretically, we can't draw the actual structure of any molecule, but this is somewhat closer to that one. So if you do the same thing for the charges, it will be -2/3. It is divided. -2 overall charge is divided among 3 oxygen atoms. So this is the hybrid. You can put lone pairs also. 2 lone pairs are common, all oxygen atoms. And this is the structure for the hybrid. And this is never asked to draw in exams. Why? Because this is just a model, right? You can't draw the actual structure. That's the theory of hybridization. But anyway, this one shows you, gives you a good idea. So if you follow the same thing for the oxalate, oxalate is having 4 resonance structures. That means 4 different ways are there to draw this one. Let's show that. You can put the 2 double bonds downward. The exact opposite of this one. And then you have 2 more options. You can put double bond here and the double bond there. That is your other option. There is other one for this. The reverse one. Like this. Understood? So 4 structures are there. Therefore, the real oxalate ion is a resonance hybrid of these 4 structures. So what is the real structure? You have this single bond, and then you have to divide this pi bond among the structures. Now, we're drawing it like this. Okay, and the charge. Now, actually, how many pi bonds are there? Yeah, we have to divide 2 pi bonds. Let me check. Here you have 2, 1, 1, and 2. So when you divide, then you can just add and see, no? 2 plus 1 plus 1 plus 2 divided by 4. 4 is the total structures. So 6/4, 1.5. So that dot represents 0.5. So this is actually representing 1.5. So if you do that same theory here, so you step this certain place, you have 2 plus 1 plus 1 divided by 3, which is 1.33. 4/3, 1.3. So this represents what? 1.33. So what do we call this one? We call this as the bond order. Bond order. Bond order. So if the bond order is higher, now let's link it to the bond length. Okay, so bond order is, here the bond order is 2, you can say. It's a double bond. So if the bond order is higher, bond length is shorter. So which one is longer? Oxalate or carbonate? Carbonate is longer. Why? Because bond order is low, therefore bond length is higher. Can you understand? It has more single bond character. More single bond character. I hope you understand that one. If you have more doubts, you can put a message here. It has more single bond character. Understood that one? More single bond character. More single bond character. Here the bond order is 1.5. That means it has more double bond character than carbonate. So then the bond length of this one will be shorter than the carbonate bonds. Okay, but it is longer than carbon dioxide. It is having 2. So like that, you can easily compare this one using bond order. It's a very good theory. Not only bond length, they are expecting here the resonance, structures, everything. That's why this paper is exam level. It's hard. Yeah. Okay. So study and learn up to these points. Repeat the paper again and again and again. Okay. So then that statement is correct. That statement is correct. So CO bond length increases in the order of this way. That's correct. Okay. If you have to check our papers previous ones and I'll give you a plan how to revise them within January and February. One more time. Follow that one. If you have a very strong general chemistry knowledge, it will be very helpful for you to learn other theories. You will understand when we do it, when we do inorganic chemistry. Most of these unit 1, unit 2 theories are there. So if you have good knowledge about those lessons already, then you can easily understand inorganic, not only that, organic, the next lessons. Okay, look at the fourth one. Oxidation number of nitrogen. Sorry, not the number, sorry. Bond angle. We'll finish that first. Bond angle of these three. So bond angle is also affected by, like we explained earlier, in VSEPRT theory, bond angle is affected by electron pair geometry. So first of all, let's draw these three species and get their electron pair geometry. So what are the species here? SO3 2 minus, SO4 2 minus, and SO3. These are the species. So let's draw them and get their Lewis structures. So this is SO3 2 minus. This is the Lewis structure. And then SO4 2 minus, like this, oxygen should have the negative charge. Okay. And then SO3, this one. This one. Okay, so these three structures are there. Then what are their electron pair geometries? Now this one is having one lone pair and three bond pairs. So double bond I earlier asked you to consider as one repulsion unit. No? So one lone pair and three bond pairs. So 4 repulsion units. Here also 4 repulsion units. So tetrahedral. Tetrahedral. So for tetrahedral, you have 109.5 degree bond angle. This one also 109.5 degree bond angle is there for tetrahedral. That is the ideal bond angle. We call it as ideal bond angle. Okay. But there is a difference between here. No? So there is a lone pair. Lone pair. So lone pair has more repulsion. Why? Why lone pair is having more repulsion? Because the lone pair 2 electrons are very closer to the central atom. Now look at a bond pair. Bond pair electrons are distributed between central atom and the peripheral atom. So central atom, peripheral atom, both are attracting the bond pair electrons. So bond pair electrons are not very closer to the central atom. But on the other hand, lone pair electrons are only kept by central atom. So there's no one else to attract them. So lone pair electrons are very closer to the central atom. And if they are closer to the central atom, that means they will occupy a greater space around the central atom. Okay, if they occupy a greater space, that means it will affect other repulsion units more. Understand? So that means they will repel other repulsion units more because they are very closer to the central atom. Simple. Understood? So as a result, if you are measuring the bond angle here, here or here, so it's a resonance hybrid, both angle should be same. Alright, so just understand that one. So my point is it should be lower than the ideal bond angle. So we generally get an estimation of the bond angle by subtracting 2.5 degrees. So that's why I ask you to do. If your school teacher said a different value, use that one, no problem. It's just an estimation. Not a hard and fast rule, ne? It's an estimation. So what is the angle? 107. Angle is a little bit lower. But there are no lone pairs around sulfur here. No? So then 109.5 angle stay there. Exactly 109.5. You might wonder whether the lone pair is affecting, but for this molecule, actual structure is a hybrid, like I explained earlier. Earlier question, remember? Are partial 5 bonds and everything. So bonds are same no? For the hybrid. Then exactly 109.5. For this one also, 3 repulsion units are there. No lone pairs. So 120 trigonal planar, the geometry. Trigonal planar. So therefore 120 bond angle. So now you can see bond angle increases in that order. Is that clear? Bond angle is increasing in this order. Okay. Understood that properly? Right. That's how you decide the bond angle now. Okay, so actually bond angle, bond length, electronegativity, hybridization, they all are kind of coming from Lewis structure and those theories only. So master them. So I know some of you are having kind of trouble with the second unit because you didn't practice enough. So now use this time to do that. There is no other option. Learning these theories from the very beginning is not going to help. Just follow one thing. Okay, fourth one. Oxidation number of nitrogen increases in the order. So nitrogen oxidation number increases in, they're asking in this order. So like I said, to get the oxidation number, we need their Lewis structures. Yeah, earlier question, SO42 minus bond angle is 109.5. We are not subtracting anything because you don't have any lone pairs around sulfur. One of you had asked a question. Bond pairs, they will be same, no? Just consider the hybrid, Pute. Consider the hybrid. Okay? Same bonds are there, ne? Then you consider the SO42 minus molecule. Even though when you draw the Lewis structure, there are two double bonds and two single bonds. It is not the actual thing. Ne? Hybrid will have equal bonds, same 1.5 bond order bonds. Okay? Right. Then oxidation number. What are the molecules they are asking? NH4, OH. Then HNO2. Then N2O5. You can use the mathematical method when I explained earlier to get the oxidation numbers easily, or you can draw them. But right now, for this, you don't know the skeletons of these. No? We'll learn them under inorganic. Therefore, I expected you to calculate and find the oxidation number here. Okay. So how do we do that one? Nitrogen oxidation number we don't know. There are 5 hydrogens, so plus 1 into 5. 1 into 5. And there's oxygen minus 2. And if it is a molecule, you don't have any overall charge. So oxidation number will be equal to 0. If you simplify this one, you will see oxidation number is minus 3. Nitrogen oxidation number No, you will get a wrong idea here. Ne? Yeah. Okay, anyway, this is a good example. This is a good example to show you. Now, if you apply mathematical method to this one, anyway, you will end up with the proper answer. But anyway, the first answer is too obvious. No? But this one, you can see if you apply mathematical method, you will get -3. Okay, but look at this one. I'll explain you why it is wrong. NH4O, it is NH2OH, right? I think I made this. Yeah, NH2OH. Yeah, wait. NH2OH. Now you will get an idea. That means you have 3 hydrogen atoms, okay? Sorry. Then the oxidation number is -1. Now what I was going to tell you now is this. If you get the Lewis structure of the molecule, this is the Lewis structure. Actually, you don't need the Lewis structure, eh? Sorry. You can do this using the mathematical method. But anyway, look at this. If you mark their dipole moments, nitrogen is more electronegative than hydrogen, and oxygen is more electronegative than nitrogen. So it loses 1 electron and gain 2 electrons. So that's why oxidation number -1 is correct. So mathematical method is applicable. No problem on it. Right. So you can find oxidation number using that. So because I made a small mistake here earlier for apply mistakenly, that's why I got the idea. So anyway, now it is perfect. Okay, clear. Right, then like I said, this one also can be found using mathematical method. So 1 hydrogen and 2 oxygen should give you the 0 oxidation number. X -3 equals 0, X is +3. This one, if you apply 2x plus -2 into 5 equals 0. So 2x minus 10 equals 0. Then x equal +10 and +5. If you draw their structures, you will realize those oxidation numbers are correct. This is a resonance structure, Lewis structure of an HNO2, and this is N2O5. This is one structure for N2O5. Yeah, +5 is there. For N2O5, you have 9 resonance structures. I hope you remember that. We discussed that. 9 structures are there. You can change the location of 5 bonds and see. Okay, so that will be discussed in the next question. Okay, so wait. Yeah, anyway, oxidation number is fine. You know that one. Good. And go to the next question, 5th one. The electronegativity of carbon decreases. So we just discussed a question about electronegativity of the carbon. The same, another question. See, if you do these model questions, the A-level questions will be really easy. This is a model question. You can see it's just one statement. But in A-level paper 25, it was a whole MCQ. Okay? Can see and understand. So then follow the program I'm giving you. There are many students in my class. So some of you are not following the advices I'm giving. So that's a sad thing. But that's the general thing. Nobody talk about that one. But I think I should be honest with you. No? Yeah. So follow this one. Only those who listen to us and work according to how we tell, we can take their responsibility about their results. Okay, so what about the electronegativity explanation? Now, like we said, we start with the Lewis structure. These are the Lewis structures, the bond structures for the easiness here. Yeah, if you check the carbon atoms, hybridization, This is linear, so sp hybridization 50% S character. Trigonal planar, sp2 hybridization 33.3 S character. Here also the same, trigonal plane. And this is tetrahedral, 25% S character. So you can see the lowest S character carbon has become the least electronegative. Then to compare between these two molecules, you have to go to the oxidation charge. So you can see there's no charge on carbon. You are checking the charge on carbon, okay, the given atom. Then check the oxidation number. So if you check the oxidation numbers, here it is losing 4 electrons partially, so oxidation number is +4. And here it is losing 3 electrons partially and gaining 1 electron partially. Then oxidation number is not +4, it is +2. Gain 1, loss 3. Remember, I explained it enough. Gain 1, loss 3. So oxidation number is +2. So oxidation number is lower here. So therefore, it is less electronegative. So this order is correct. Can you understand? Now, once you learn it properly, slowly, apply it here. Same thing. Okay. Now that question comes to an end. Okay. So we can go to the question number 9. Question number 9. In question number 9, it is asking which of the following species shows a linear shape. Linear shape. That means it's kind of a checking a theory we have revised today. Lewis structure, VSEPR theory. Lewis structure and VSEPR theory. So what are the three molecules or species? O3, I3 minus, ClO2 minus. It's a good example to tell you important thing. And SO2 and then NH2 minus. NH2 minus. Okay, O3. So skeleton and the Lewis structure is this one. You follow the Lewis method I revised, practice it more, then you will get this structure. You can try this one. When you are looking the video, you can pause the video and draw it according to the theory note. Theory note, it is explaining you the Lewis method, no? So according to the Lewis method, get a skeleton and then find the total valence electrons and try that one and then see whether you get this one. Okay, like that, try it for the others too. So here also one iodine atom is central. You will get a structure like this. When a group 17 element comes as the peripheral atom, it always makes single bonds. Okay? Group 17 always, you will realize that when you practice. I don't like you to remember it. And then there are 3 lone pairs. There are 3 lone pairs. This is the structure. And like I said earlier, there are 5 repulsion units, 3 lone pairs and 2 bond pairs. They are arranged in trigonal bipyramidal electron pair geometry. Okay, now I want to tell you about this one. Okay, so here you can see the negative charge is there on oxygen. Some students get stuck when they try to draw this one. Here you have a negative charge, I forgot to mention. Now look at this one again. Some students are getting stuck when they try to draw this one. Why? The thing is, Cl here, sorry, oxygen here is having a negative charge. One oxygen is negatively charged, so that negatively charged oxygen should be like this. And there is another oxygen atom that should not have any charge in the stable structure. It should be making a double bond. Can you understand? So 2 oxygen atoms should be like this. So if you put that one for the chlorine, you're having like this. Then chlorine was having 7 valence electrons. But here only 3 is represented. So other 2 valence electrons should be like this, no? or you can put them in the other sides, no problem. I'll later explain that. Okay, so this is the Lewis structure. And SO2, a similar one. There's a lone pair on sulfur. And NH2 minus. There are two lone pairs on nitrogen. Now, if you just look at the things I have drawn, it will be now looking like linear, no? These three, according to the way I draw. But it is not the actual shape of the molecules. Okay, so actual shape of the molecules are decided by the VSEPR theory. VSEPR theory. Okay. Now here, how many repulsion units are there around this oxygen? There are 3 repulsion units. So, trigonal plane electron pair geometry, and if you are having one lone pair, so this becomes bent shape. It's the red color. This is bent shape, bent or angular. Sometimes it is mentioned as V shape also in some books. It's not commonly used in A levels, however. But anyway, no, bent or angular, that's the most common words. And this one is trigonal bipyramidal. Trigonal bipyramidal electron pair geometry. Now, if you want to check the shape, okay, shape, depending on the lone pairs, shape is going to change. No? If you are having one lone pair here, then it will be seesaw. If you are having two lone pairs, like we saw in earlier questions, it is T-shape. Now, if you are having three lone pairs like this, then it is going to be what? Linear. That is our answer. So, linear shape. Linear shape. Linear shape. Can you see? So, lone pairs are not visible no, when you check them. I mean, you're not actually looking at the iron or molecule. Okay, there are other methods. Just don't worry about them. Just imagine you are looking at this one. You're not going to see the lone pairs. No, ultimately you are seeing the nuclei of 3 iodine atoms. No? So nuclei of 3 iodine atoms are arranged along a line, straight line. So that's why we call it as linear. Simple. Linear. And then don't mistake this one. So I said later I'll explain. This is drawn actually like water molecule. There are two lone pairs here. The lone pairs are there in the same side. Okay. So then this is coming from tetrahedral electron pair geometry. If you are having one lone pair, then it is pyramidal, trigonal pyramidal. If you are having two lone pairs, it will be again angular or bent. Okay, so don't mistaken, if even though they have the same names, angles are different. This is having even a lower angle. Okay, 109.5. Subtract, there are two lone pairs. So 2.5 into 2, 5 degrees. So 104.5. But this one, 120 minus 2.5. So estimated angle is 117.5. See, two angles, okay. But the same name, it's angular. This is also angular. See, related similar to those one. And this one is also similar to this one. Just like water molecule, it is having 104.5 one angle. Can you see? So anyway, the linear shape is given for I3 minus. I3 minus. So I3 minus is our answer. I3 minus is our answer. Now for the earlier questions, I'll update this PDF and add to your group also. You can save that too or take a print out of that one. So put your effort on things necessary only. Okay. I3 minus. Yeah, then let's go to the 10th question. It's asking about the stable Lewis structure. Stable Lewis structure. Okay, so the number of stable Lewis structures that can be drawn for iron HP2 HP2O6 2 minus HP2O6 2 minus, sorry, 3 minus. So luckily they gave you, not luckily actually, that's the way they asked only. They gave the Lewis structure, but there is a small mistake in the Lewis structure. Okay, so it's not correct. You will see some lone pairs are missing, but that will not affect our answer. Okay, so what is the Lewis structure? H, P double bond O and another O. O, central oxygen is also there. And there is double bond O here. Okay, so the correct Lewis structure should be something like this. This oxygen should have 3 lone pairs and a negative charge. This oxygen also should have 3 lone pairs and a negative charge. Here you should have 2 lone pairs. It is not shown. Here 2 lone pairs. Here 2 lone pairs and here 3 lone pairs and a negative charge. Don't put anything there. Okay, so now they're asking number of stable Lewis structures. Now this theory is about resonance. Now, like I said earlier, you can draw different Lewis structures. Okay, now we draw earlier carbonate Lewis structures and oxalate Lewis structures. Okay, but here also you have Lewis structures. You can draw Lewis structures, but there's a theory behind that one. When you want to draw stable Lewis structures, you have to change the location of the fiber. So what's the theory? Change the location of the fibers. Change the location of the fibers. By changing the location of the phi bonds, we can take different structures. Okay, so now for example, if you take this one, it has a double bond here, so I'm going to keep the double bond there. But in the other side, okay, so I'm going to change the location of the double bond. I'm going to put it there. First one. Okay, and then I'm going to draw this again. I'm going to put the double bond here. Then the negative charges will go to the other ions. And actually these 3, you can see now. By keeping the double bond here, I can take 3 structures. 3 structures means the given one also we have to count. No? Given one also we have to count. So there are 3 structures. So now you can see by keeping the phi bond here, I'll mark it again. By keeping the phi bond here, we change the location of the other phi bond. We change the location of the other phi bond. Can you see? So we can do the same thing. So we get 3 structures now. We can do the same thing by changing the location of this phi bond to here. Then again you can put other phi bonds into these 3 places. So that means you will get another 3 structures. Get the idea? So to your review, if needed, you can draw all these 6 structures according to the way I told you. Now by keeping the double bond here, you draw 3. Right? And by putting the double bond to the other place, understand it properly, putting the double bond here, you can draw again these 3 structures. Okay, double bond will be shifted to the other place here. Understood? So you'll have 6 structures. 6 structures. Okay. So these 6 structures are stable. Stable means what? Stable means what? Now, you know, here we have negative charges, right? But all those negative charges are there on oxygen. Oxygen is a very good high electronegative element. Oxygen like to keep electrons, so it is given electrons. So it is stable. Understood? Stable. Low energy stable. Okay, because more electronegative atom has the negative charge. But let's say when you want to alter the location of the 5 bonds, if the oxygen gets a positive charge, when we do that, that is not a stable structure. Okay. So now when you change the location of the 5 bonds, as I said, if you came across a structure like this, let me draw and show. If you got a structure like this, then what it will be? Here you will have a positive charge on oxygen. So having positive charge on oxygen is it good? No, it is unstable. So unstable. Why? Because more electronegative oxygen has a positive charge. So it's not a good thing. Okay. And the charge is also distributed everywhere. So that also not a good thing. Okay. So there are two reasons for this to be unstable. Higher charge distribution and more electronegative oxygen having the negative charge, positive charge. Sorry. There are more reasons. So therefore, this one is not stable. Get the idea? So, but the question is asking only the stable ones. Stable ones. That means it is only asking the 6 structures I mentioned. Okay, Pute? Therefore, the answer here should be answer 4. Answer 4. Is that clear, Lamai? Answer should be answer 4. Okay, so number of stable Lewis structures that can be drawn for HP2 or 6,3 minus is stably you can draw 6 structures. If you think about the total number of structures, there will be many, but all other things will be unstable. Understood? All other things will be unstable. Get the logic here. It's a good question. They have asked similar past paper questions to this one in new syllabus. So knowing that will be helpful. Okay. Okay. So now we discussed today 10 MCQs. Okay, so I'm going to finish the discussion from here. I wanted to explain the whole picture. I didn't had a good idea regarding how many questions will I be able to explain. That's why I didn't set any limit here. Okay, by when we start. So we took nearly 3 hours. Okay. And we like a theory class, ne? And we discussed 10 MCQs. I hope we went to every detail, every possible detail, even a tiny theory part was explained. But still, if you go to your theory book and query for the recordings, you will see there are more, right? That's how it is, right? And go through them as well, right? Especially with the theory note you have. If your theory note is not complete, you can ask help from a friend and complete it. And more importantly, write a good review for this one. Don't stop there. That's why I'm frequently telling, refer those reviews again and again and again, because the same mistakes you will learn, you will make the same mistakes again and again and again. Okay, so if you want to correct them, refer your reviews that you have written. Okay, so I'll tell you another day, and in that day, maybe sooner, I'll check where I can find some time. Anyway, I'll put a time to your group and we will discuss other questions like this. It seems like for like 3 hours, we can discuss 10 MCQs in this level. So let's discuss other 10 MCQs. Now, question number 11 and 13, those are kind of chemical calculation questions. We didn't touch chemical calculations today. Our main focus was there on unit 1 and unit 2. Unit 2 mainly. Unit 2, you learn basically the whole unit, right? Without secondary interactions, right? So anyway, my point is, from our next day discussion, we can cover mainly the calculation theories. Okay, and yeah, the redox balancing is there in question number 17. I'll remind redox balancing fully in that discussion. and ionic radius is there, so we can discuss periodic properties. And 2 questions about gases are also there. See, question number 15 and 18. So we can just remind some gases theories too. Okay, so from the next 10 questions, we will try to recall them, those theories. Okay, right. So I'm going to upload a PDF that is having these questions, answers for this question. If you want a small review, you can go there. Right? If you want a small review, you can go there. I'll upload the PDF soon. Then, if any student, okay, I'm doing this one for the student at a very base level. Okay, let's say who miss a lot of things and who didn't understand it still. Okay, so can get a great benefit from this discussion. Okay, you might felt the difference. When we usually discuss a paper, we don't take this much time. Usually within 1 hour, we finish 10 MCQs, right? But today we took more time and right, because that is need to be done. So in case someone needed, right? So let's finish the discussion for today. I'll tell you another date, like I said. So see you again on that day. Study well and remember, write a good review. Okay. Right. Goodbye, Lamai.